from the values of the partition function that it increases like an exponential function. We already see this behavior as n tends to infinity. P of n is behaving like an exponential function divided by this 4n root 3. So that's why it goes so fast. Now let us look at what the generating function for P of n is. And this goes back to Euler. But before I discuss this, I would like to give the definition of a generating function that was given by Herbert Wilf, or not a definition, but a quotation. So Herb Wilf wrote that a generating function of a sequence is a clothesline on which you hang all elements of the sequence. It's like a hang, it's the rod on which we have the clothes put through the hanger. Now, if you want to carry all of the clothes together, you just take the hanger and we go from one place to the other. And then all of the clothes are taken in one go. So what he's trying to mean is that if you want to understand properties of a sequence, then you can also do so all at once by studying an analytic function, which is the generating, you can, let me not say analytic function, analytically you can talk about generating function of that sequence, and which carries all of the information about that sequence, and you can work analytically with it. So what did Euler do? Euler found this beautiful formula. The generating function is on the left. The summation n equal to 0 to infinity, P of n, q to the n. And in the long hand, you can write it as P of 0 plus P of 1 times q plus P of 2 times q square plus so on. So what Euler showed that this generating function is given by this infinite product, 1 upon 1 minus q times 1 minus q square times 1 minus q cube and so on. Now here q is a complex number with mod q less than 1. This is required for the convergence of the infinite product. I'm going to not discuss about the convergence aspects here. Let us not go into that detail, but whenever they are essential, I'll just point out to those. So the important thing is to know how we get the second equality. So I start with the right-hand side, this infinite product, and I write it as 1 upon 1 minus q times 1 upon 1 minus q square times 1 upon 1 minus q cube and so on. We have mod q less than 1. So mod q to any power is less than 1. We can expand all of these functions in terms of the geometric series, and that's what you see on the right-hand side. It doesn't end there. There are ... which is unfortunately not seen. Okay, so I write this together in this form. We have this multi-sum with infinitely many indices of summation, n1, n2, n3, all going from 0 to infinity. And we have q to the 1 times n1, that's deliberately written in that way, q to the 1 times n1 plus 2 times n2 plus 3 times n3 plus ... Now I would like to convert this multi-sum into a single sum. I'm going to let 1 times n1 plus 2 times n2 plus 3 times n3 plus ... to be equal to n. If I do that, obviously, because n is finite, after some point onwards, you will have all of the ni's equal to 0. If you start with a very big number, n is 10 million, say, you may have to go far enough, like your I will be very high, so that from that I onwards, I plus 1. If you consider ni plus 1, all of them will be 0. So all but finitely many of these ni's are equal to 0. Now, the question is, if we write it as a single sum, of course, we see there q to the n by using this equation 1. But then the important question is, what is the coefficient of q to the n? Now, in order to answer that, let us attach a meaning to each of these ni's. Now, this is where combinatorics reach them. So, what's the meaning that we are going to attach? The ni is going to denote the number of times I will appear in a particular partition of n. Okay. So, for example, if my n is equal to 4, what all possible combinations I have? I can take n1 to be 4 itself and all of the n2, n3, n4 onwards to be equal to 0. But then that gives me the partition 1 plus 1 plus 1 plus 1, because there are 4 ones. But I could do n1 as 2 and n2 as 1, and then all of the n3, n4 as 0. So that will give me 1 plus 1 plus 2. So that is a partition 2 plus 1 plus 1. So by attaching this meaning that ni is denoting the number of times I is appearing in a particular partition of n, each partition is uniquely represented on the right hand side, and so how many times we'll be getting q to the n is exactly equal to how many partitions of n there are, and that actually does it, because then the right hand side is becoming summation n equal to 0 to infinity p of n q to the n, and that's Euler's generating function. Now, what can we do with the help of these generating functions? There are quite many things one can do. Let me give an illustration. Let me start with an example. If I start with the number n equal to 6, then how many partitions of 6 there are? There are 11 of them. 6, 5 plus 1, 4 plus 2, 4 plus 1 plus 1, and so on. You can see all 11 listed here. Now I'm going to put restrictions on the number of, on the parts which are there in this partition. For example, if I ask, I want to only consider those partitions of 6 where the parts are always odd. So naturally, only 4 of them survive. You can see we cannot consider 6 because 6 is an even number. So the first partition that qualifies is 5 plus 1, then 3 plus 3, 3 plus 1 plus 1 plus 1, and then 6 ones. All of these partitions have only odd parts. Okay, so there are 4 in number. Now I ask another question. Let me consider only those partitions of 6 in which the parts do not repeat. In other words, I want partitions of 6 into distinct parts. And these are also 4 in number because 6 itself, 5 plus 1, 4 plus 2, and 3 plus 2 plus 1. Everywhere else, we see that there are repetitions. Like 3 plus 3 does not qualify because there are 2 3s. So these are also 4 in number. Is this just a coincidence, or is it a property of every natural number, not just 6? Of course, it's not a coincidence. This is a theorem of Euler that the number of partitions of n into odd parts always equal the number of partitions of n into distinct parts. Let us see how we can prove this. We cannot go ahead one by one, starting with every natural number n and showing that, okay, you get the same every time, same number every time. So we have to do this once for all. So one way is to create a bijection from one set to another. Now you have a set of all partitions into odd parts. You have a set of all partitions into distinct parts. And you create a bijection between the two sets so that they have the same cardinality. That's one way. But the other way is by using a generating function. And here is how it can be done by means of generating function. So let me denote A of n and B of n as the cardinality of those two sets. The number of partitions of n into odd parts is denoted by A of n and the other one by B of n. We show that these two infinite series are equal. By linear independence of the monomials, this will imply that an equal to bn for all natural numbers. So if I look at the generating function of this, that is what is given by equation 2. And why is that? Because you see, I only want partitions into odd parts. So in the denominator, I have deliberately removed 1 minus q square, 1 minus q to the 4, 1 minus q to the 6, because those are giving me how many times 2 appears in my partition, how many times 4 appears in my partition, and so on. But I don't want even parts. So I'm just putting 1 minus q, 1 minus q cube, 1 minus q to the 5, and so on in the denominator. Similarly, when I look at partitions into distinct parts, I claim that the right-hand side of equation 3 is what we get as the generating function. Why is that the case? So if we look, by the way, is the last line visible? That 1 upon 1 minus q to the n. Is that visible? Sudipto?
So maybe you can use
hide
the
that.
height.
Okay.
That's yeah.
Okay. So 1 upon 1 minus q to the m. Of course, if you expand it in the geometric series, you have 1 plus q to the m plus q to the 2m plus q to the 2m, so on. That 1 I am writing as q to the 0 times m. Then the next term I'm writing as 1 times m, q to the 1 times m, and so on. So if m appears in the partition, if I want a partition into distinct parts, what does that mean? Either that part does not appear at all, or if it appears only once. So in the right-hand side of this last equation, I have to remove everything except the first two terms, q to the 0 times m plus q to the 1 times m, because either m appears and then it appears only once, or it doesn't appear at all. And that's the reason why on the right-hand side, you don't see in the first factor q square, q cube, and so on. You just see 1 plus q. In the second factor, you don't see q to the 4, q to the 6, and so on. You just see 1 plus q square, and so on. Okay, so now I have constructed the generating functions for these two infinite series. And now my job is to show that the right-hand sides of equations 2 and 3 are equal. So now here again, we are dealing with infinite products. So ideally, how we should be going is to truncate them and then let that upper index of in the product go to infinity. So that is how one should do. But let me now do it formally for this talk. So I start with the left-hand side, and I simply include the missing factors. So I multiply top and bottom by 1 minus q square, 1 minus q to the 4, 1 minus q to the 6, so on. And then in the bottom, I have 1 minus q. In the top, the first factor is 1 minus q square. So I just use the elementary identity a square minus b square is a minus b times a plus b. So here, I cancel the 1 minus q, so I get 1 plus q. When I cancel 1 minus q square, I get 1 plus q square, and so on. So that gives me the right-hand side, and that proves Euler's theorem for all natural numbers and all at once. Okay, is this just something that is done for the sake of fun, or does it have any applications? Let us look at some areas where partitions surface. So non-parametric statistics, probability and statistics, particle physics, asymptotics and partition identities, computer science, group theory, everyone knows about Young tableau. And then in areas which are related to this theory of partitions in number theory, we have basic hypergeometric series or modular forms, or the recent field of mock modular forms. I'll talk about that also later. So let me see who were the people who initiated this theory. Of course, you have Euler. There were some developments done before Euler also, but a systematic theory of partitions begins with Euler. Then Gauss made important contributions, Jacobi. Then the English mathematician Sylvester played a very important role, but this role was played when he moved from England to US in Johns Hopkins, where he helped set up the department as well. He made some very fundamental contributions in invariant theory and also in partitions. Few more, G.H. Hardy, Ramanujan. And then in the contemporary partition theory, we have one of the major figures is George Andrews and late Freeman Dyson, who just passed away a couple of months back. Everyone knows he's a star physicist as well as a star mathematician, and he contributed greatly to the theory of partitions. And I'll be coming to Dyson's contributions in some time. Okay, let us see this story again between Hardy-Ramanujan and McMahon. So Hardy and Ramanujan thought of approaching partitions analytically. They wanted to construct a formula for P of n, and you just put n, however high it may be, and that gives you an answer. Whereas McMahon was asked by Hardy and Ramanujan to actually compute up to n equal to 200. It's a very painful process. McMahon actually used this recurrence relation of Euler to compute P of n up to n equal to 200. And it took him about a month to reach P of 200. And it is important to note that this table was extended by Hansraj Gupta, an Indian mathematician, up to n equal to 300. Now, this is pre-computer days. So nowadays in Mathematica, by just a click of a button, you can get P of 1000 as well. But this was back in 1910s, and Hansraj Gupta's work, I guess, is around late 1930s or 1940s. So McMahon took about a month to calculate P of 200, and what McMahon did was he wrote the values of P of n in groups of 5. For example, he had P of 0, P of 1, P of 2, P of 3, P of 4, then he put a line. Then he started with P of 5, P of 6, so on up to P of 9, he put a line, and so on. And then he gave the list to Hardy, who gave it to Ramanujan. So the list was with McMahon, who prepared it. The list was also given to Hardy. He had it in his possession for a few days. And then it was given to Ramanujan. But neither McMahon nor Hardy noticed what Ramanujan found. Ramanujan just looked at the number above that line that McMahon wrote after groups of 5. So that number is of the form 5n plus 4. What Ramanujan found was P of 4 is 5, P of 9 is 30. And in general, he found that P of 5n plus 4 is always divisible by 5. I mean, at least up to n equal to 200, he saw that this is what is observed. So that led him to conjecture that P of 5n plus 4 is always congruent to 0 mod 5. Now, if someone doesn't know this definition, I have recorded it below. A congruent to B mod M implies M divides A minus B. This is an equivalent way for writing M divides A minus B. So what is this saying is that 5 divides P of 5n plus 4. Now you may say that, okay, there is nothing great in Ramanujan's observation because McMahon already put it in groups of 5. And so this was quite easy to see. But Ramanujan also found that P of 7n plus 5 is congruent to 0 mod 7, and P of 11n plus 6 is congruent to 0 mod 11. That were quite curious observations. Later on, he proved all three of them, but he didn't stop there. Here is what he proved. Hardy calls this as the most beautiful identity of Ramanujan. So Hardy says that if I have to pick one identity from the whole of Ramanujan's work, then here is what I claim as the most beautiful identity of Ramanujan. And that is a generating function for P of 5n plus 4. So it is given by the infinite product on the right-hand side, and you can see clearly the 5 appearing in the front. So once one proves this identity, the first congruence follows trivial. And there are corresponding identities for 7 and 11 also, but the one for 7 involves two such infinite products. The first one contains 7 in the front, and the second contains 49, but still divisible by 7. And the one for 11 is quite complicated. In fact, such a generating function was developed not too long ago, maybe 3-4 years back. Anyway, but Ramanujan had proved all three of them in a different way. And he also wrote that it appears that there are no equally simple properties for any moduli involving primes other than these three. What do we mean by that? When he says simple property, he is meaning that if you take this modulus, p equal to 5, the arithmetic progression here, 5n plus 4, also has as its modulus this 5 itself. If you have 7 here, you have 7 itself. You have 11 here, you have 11 itself. And he is saying that these are the only 3 primes for which you can have such a result. Now, Ramanujan wrote this just as a one sentence in his paper, but this was not proved until 2003 by Scott Algren and Matt Boylan in an Invenciones paper. It uses filtration theory of modular forms. But if you do not restrict that the same prime appears on the other side, or the same number, let us not discuss even primes. Suppose I have some number here, 12, and I'm okay with having the modulus of the arithmetic progression as any other number. Then it was proved by Ken Ono in 2000 in an Annals of Mathematics paper that there are infinitely many such congruences for L greater than or equal to 5. The L equal to 2 and 3 are more subtle, but let me not go into that. Okay, so we have seen this congruence is true, Ramanujan proved it. But as a 16-year-old student, Freeman Dyson, he asked a fundamental question. Can I have a statistic by means of which I can see how these partitions of 5n plus 4 are equidistributed in 5 equinumerous classes? You are saying that 5 divides P of 5n plus 4. Can I define a statistic by means of which, let's say I have 5 buckets, and I can put each of these partitions of 5n plus 4 in each of these buckets, and you see each of these buckets have equal number of elements. So that's what he asked. And he did find this statistic. This statistic is called as rank of a partition. And it has a somewhat unusual definition, because on one side you are considering largest part and then minus the number of parts. So what the largest part actually is also counting, and how many parts you have is also counting towards the definition. So the rank of a partition, Dyson defined as largest part minus the number of parts. And with the help of this rank, he was able to show that you have P of 5n plus 4 into 5 equinumerous classes, and those of 7n plus 5 into 7 equinumerous classes by means of examples. Okay, for few numbers of the form 5n plus 4 and few numbers of the form 7n plus 5. He did conjecture later on in general, and that was proved a few years back. But let us not discuss that first. Let us see an example. So L of pi here denotes the largest part, and hash of pi denotes the number of parts of a partition pi. So let us take the 7 partitions of 5 again. Let us compute the rank of each of them. So let us consider the partition 5. The largest part is obviously 5. The number of parts is just 1. So the rank is 4. The largest part is 4. The number of parts is 2. It's 2. Largest part is 3. Number of parts is 2. 1. Here 3 minus 3, 0. 2 minus 3, minus 1. 2 minus 4, minus 2. And 1 minus 5 is minus 4. Now if you look at all these numbers modulo 7, then you can see that every residue class appears one and only once. That actually shows that the partitions of 7n plus 5, the partition of 5, that is when n is equal to 0, is divisible by, P of 5 is divisible by 7. In fact, it is equal to 7. In general, he conjectured that, let me explain this notation first. This denotes the number of partitions of 7n plus 5 with rank congruent to 0 mod 7. He showed that that number is equal to the number of partitions of 7n plus 5 into rank congruent to 1 mod 7, same as here, 2 mod 7, and so on up to 6 mod 7. So what I just showed you, but in general. So he conjectured this, and also for 5n plus 4. But one important thing is that Dyson found that this failed for 11n plus 6. If you consider, for example, n equal to 0 here, and just consider partitions of 6. We know there are 11 in number. We have seen that before. So if I calculate rank of each of these 11 partitions of 6, and I look at them modulo 11, I do not get every residue class one and only once. So this rank does not distribute the partitions of 11 and plus 6 into 11 equinumerous classes. So he said that he hypothesized existence of another statistic that he called as crank, which would give a combinatorial interpretation of this congruence, which would say that, okay, here is how you get modulo 11 each and every residue class if you classify them on the basis of this crank. But he did not know what this crank is. So he said that this is probably the first instance where an arithmetic function has a name even before it is defined. And very nicely, he ends his paper by saying that may it be preserved by the ignominious fate of the planet Vulcan. But of course, the fate of crank was not as bleak as planet Vulcan. We'll see that very soon. But what I want to say is that Dyson's first paper, the very first published paper, considered in mathematics or in physics, that was on partitions, this 1944 paper where he explained rank and he hypothesized crank. His last paper on partitions, I believe, was in 212. So you see the span of his work. I'm sure in physics, as well as in mathematics, he published until he died in 2020. So Dyson's conjectures were proved by Atkin and Swinnerton-Dyer, two English mathematicians. Atkin died in 2008, whereas Swinnerton died recently in 2018. Now, crank was found after 44 years. In 1988, Frank Garvin, as a PhD student under George Andrews, he found the vector partition. So the discovery of crank is also quite interesting, and I would like to take a minute to explain it. So at University of Illinois at Urbana-Champaign in 1987, there was a centenary to celebrate Ramanujan's 100th birthday, and there was a conference to celebrate Ramanujan's centenary, and there were many mathematicians from all over the world who attended it, and so did Andrews and Garvin, and the two of them were supposed to leave the next day after the conference ended. And after the conference ended, they both went to their rooms in the same hotel, and they called one another and they decided to work on this crank. And by the end of the night, they were ready with the definition of this crank. And Krishna Swami Allah, one of the partition theorists, he very nicely claimed that probably it was the desire of Namgiri Devi of Namakkal that this discovery of crank would be done when the Ramanujan Centenary Conference is being held. So anyway, this crank for actual partitions was found out in 1987. The paper appeared in 1988. Initially for vector partitions, which I'm not going to define, Garvin did have a crank, but not for ordinary partitions. Okay, let me now move on to what is known as the Hardy-Ramanujan-Rademacher formula for P of n. So we have already seen this asymptotic. The partition function goes very fast. But Hardy and Ramanujan's formula was an asymptotic formula. Whereas Rademacher just made few improvements to it, and he was able to find an exact formula for P of n as this particular infinite series, where this ak of n is given by this sum. It's a Kloosterman sum, and this I is the I Bessel function, the modified Bessel function of the first one. So this looks, when you see this for the very first time, it's a completely crazy formula, because on the left-hand side, you have an innocent function like P of n, where you are just counting how many partitions of n there are. On the right-hand side, you have a formula where analysis creeps in. You have special functions in there, because you have modified Bessel functions, and then infinite series, and even the function ak of n is quite involved. So it's quite interesting how Hardy and Ramanujan first envisioned this asymptotic expansion, and Rademacher improved it to get to an exact formula. Also, Sylvester did get it at the same time, but Rademacher published this further. Rademacher published this before Sylvester, and then Sylvester did not publish it at all. Okay, so now I would like to move to combinatorial aspect of partitions. So we have seen this analytical aspect. We have also seen the aspect by means of generating functions. Let's see how combinatorics also creeps in. So here is a theorem of Euler, very famous theorem. It's called as Euler's pentagonal number theorem, because the numbers here, when n is going from minus infinity to infinity, so these numbers are called as generalized pentagonal numbers. Okay. So what Euler had proved was, if you consider this bilateral series going from minus infinity to infinity, it's it is given by 1 minus q, 1 minus q square, 1 minus q cube, so on. This is exactly the reciprocal of the generating function for the partition function. Okay. Now Legendre observed that if you look at coefficients of q to the n on both sides and compare them, then you get an arithmetical equivalent of this identity. And that's quite interesting because it has an explanation in terms of partition. So what you are doing is you are taking a positive integer n, you are looking at partitions of n into distinct parts, then you classify them into two parts. Those partitions of n into distinct parts with even number. So even number of distinct parts, that will be denoted by dE of n, and the number of partitions of n into odd number of distinct parts, that will be denoted by dO of n. Then dE of n is almost always equal to dO of n, unless your n is a generalized pentagonal number, in which case they differ by only 1. So they are almost always equal, and when n is a generalized pentagonal number, either this is bigger than dO of n by 1 or less by 1. So Franklin, a student of Sylvester, he found a purely combinatorial proof, that is without using generating functions, without using any analysis. What he did was, he found a way, which is, you cannot call this as a bijection, but you can call it as an almost bijection between the set enumerated by dE of n and the set enumerated by dO of n, because they are almost always equal. So almost always their cardinality is the same, in which case you have an actual bijection, but it's not true when capital N takes this form. So this is how he proved this, and I would like to give proof of this because it's quite interesting. Let me denote by lambda this particular partition, lambda sub 1, lambda sub 2, so on up to lambda sub r. So in the canonical form, we will have lambda 1 greater than or equal to lambda 2 greater than or equal to up to lambda r. So this is the smallest part, and denoting that by S of lambda. S of lambda is lambda r. And then sigma of lambda I'm denoting as the number of consecutive integers in the sequence starting from lambda. So suppose this, let me start by means of an example. If I consider lambda to be this partition 7, 6, 4, 3, 2, then what will be sigma of lambda? It will be 2. I start from 7, and how many consecutive integers I can find? That is my sigma of lambda. So if there was a 5 in between, then my sigma of lambda would have been 6. 7, 6, 5, 4, 3, 2. But there is a 5 is missing, so my sigma of lambda is 2. Okay. And my S of lambda is 2 as well. So we are going to consider two cases. If I consider this particular partition of whatever these things sum to, 13 plus 7, 22. So this particular partition of 22, it's a partition into distinct parts, and it's a partition into odd number of distinct parts, because I have 5 parts, so it's an odd number. Note that the part itself can be even, but the number should be odd. In this particular case, it is 5. So this is something which is enumerated by DO of 22. So I just write this in terms of what you call as a Ferrer's diagram, just representing each part by means of dots. So these are 7 number of dots, 6, 4, 3, 2. Some people, especially in computer science, you have boxes instead of dots. Okay, so what are we going to do when we are in the first case? This is what qualifies to be in the first case, because S of lambda is 2 and sigma of lambda is 2. This is sigma of lambda. This is S of lambda. What we simply do is we move these 2 dots and put it next to these. 1 dot here, 1 dot here. You get to this. Now, by doing so, of course, you have one less part than the number of parts here. You have even number of parts. So this partition is enumerated by DE of 22. So you are going from DO of 22 to DE of 22. And you still have partition into distinct parts. Otherwise, it wouldn't be in DE of 22, because we need parts to be distinct in the first place. So when I take this, if I am not getting distinct parts, then that is not what I want. But in this particular case, you can notice that that will never happen. You take this 2 on this other side, you get 8, 7, 4, and 3. Okay. And now, if I want to get a bijection, I know we don't get a bijection here, we get an almost bijection. But suppose we want to get a bijection, what is the thing that is required? When I reverse this procedure, I should be able to get this partition itself. This should not get mapped to something else. So, let us look at the second case. I'm going to consider the same partition, 8743, which was on the right-hand side here. But here, S of lambda is 3 and sigma of lambda is 2. So, it's not in the first case, that is S of lambda is now greater than sigma of lambda. What do I do in that case? I move these last 2 dots below to essentially reverse the procedure. And it looks like, okay, so always this is going to get the same partition. But I'll give you an example where it doesn't. So we don't really get always a bijection. Let us consider this particular case. My lambda is 8765. This is again a partition into distinct parts. Here S of lambda is 5. Sigma of lambda is 4 because it's a continuous sequence. It's 8765. Consecutive integers are there. Now S of lambda is greater than sigma of lambda. So we are in the second case. So we take these 4 dots and put them below. When I take these 4 dots and put them below, I don't get partition into distinct parts to begin with. Because I have this 4, remember this dot along with these 3 goes below. So I get 4 here as well as 4 here in the below. So this is not even a partition into distinct parts. So this was something which was enumerated, what is this number? 15 plus 11, 26. So this partition was enumerated by DE of 26. But one cannot bijectively map this to DO of 26. Okay. So that shows the problem of getting a bijection always. But when does this occur? Suppose my sigma of lambda is R. In this particular case, R is 4. And my S of lambda is 1 more than sigma of lambda, which is what is the case here. Sigma of lambda is 4, S of lambda is 5. What is the number that is being partitioned? I start with the smallest part. And remember, I have partition into distinct parts here. So if I have R plus 1, the next one must be R plus 2, R plus 3, and so on. And there are R of those. So the last one will be R plus R. If you add these, you get a pentagonal number, R, 3R plus 1 upon 2. So that's when this fails to give a bijection. And there is another case where both S of lambda and sigma of lambda both equal R. And there also, you don't really find a bijection. That corresponds to the case when you have this companion to the pentagonal number, and together these are called as generalized pentagonal numbers. So when n is R times 3R plus or minus 1 by 2. So they are almost always equal, but when they hit, when we have a pentagonal number n, then you don't have them equal. One is more than the other. So this is one way of proving partition identities, and this is also a very, very hot topic in this theory. It's very, very difficult sometimes to produce bijections using combinatorial techniques. There are many identities for which there are no bijective proofs known, only analytical proofs are known. But many a times, people who produce bijective proofs, they are also able to see many new constructs and many new observations than what could be seen through analytical proofs. So each one has its own pros and cons. I would like to discuss in the last part of my talk 2 very famous identities known as Rogers-Ramanujan identities. So these are denoted by, this is the first Rogers-Ramanujan identities, and this is the second Rogers-Ramanujan identity. So these are what are called as sum to product identities. But I have not told you what the definition of this is, so let me go ahead with that first. A semicolon q sub infinity is nothing but this 1 minus a times q, 1 minus a times q square, and so on. Of course, here we have to assume that this converges, and when mod q is less than 1, you have the convergence. Okay. So this one, for example, will be 1 minus q, then 1 minus q raised to 6, then 1 minus q raised to 11, and so on. 1 minus q raised to 4, 1 minus q raised to 9, 1 minus q raised to 14, and so on. So the first Rogers-Ramanujan identity and the second, what is the difference? In the numerator, on the sum side, you have only n square here, but in the second one you have n square plus n. And then here you see you have 1 and 4, but here you have 2 and 3. These identities were first discovered and proved by L.J. Rogers. Here is a photograph of Rogers, an English mathematician. And they were rediscovered by Ramanujan before going to England, sometime before 1913. But Ramanujan did not have a proof at that time. And there is a very interesting story. Many times we have seen that people in India are given recognition by our fellow Indians only when they get a certificate from some mathematicians abroad. Okay, if they say that, okay, this person has done good work, then we say, I mean, many a times we hear, I'm not saying always, but here is a case where it went reversely. So Rogers was a mathematician, an English mathematician who was barely known in the academic world. He proved this very beautiful identities in 1894, and they were completely forgotten. People were not interested in them until one day Ramanujan was browsing in the Cambridge University library, the old volumes of Proceedings of London Math Society, and he saw the exact same identities which he had obtained before going to England in Rogers' paper. And now see how this reflects on the human side of Ramanujan. Any person who sees that, okay, these two very beautiful identities that I have obtained are already proved by someone, we will be disappointed and we will be jealous about that person. But Ramanujan was so happy that he took that volume and he ran to Hardy's office and he told him, see, these identities which I had obtained without proof are already proved by Rogers. And from that time, Rogers got unprecedented fame, and he got a permanent position at the University of Leeds. And Rogers was a famous mathematician. So this time, it was someone from India who gave a certificate to an English mathematician's work, and that mathematician rose to fame. Let me not go into the proofs. The proofs are quite involved. Even though they look like simpler identities, they are very tough to prove. I won't go over proofs, but I will just mention that they also have interesting partition theoretic interpretations. So on one side, it is very easy to see that this right-hand side is generating partitions whose parts are congruent to 1 modulo 5 and 4 modulo 5. You see, in the case of the partition function, we had 1 upon 1 minus q square, 1 up minus q cube, and so on, all of them. But now we are only having 1 minus q raised to 6, 1 minus q raised to 11, here 1 minus q raised to 4, 1 minus q raised to 9, 1 minus q raised to 14, and so on. So only parts which are congruent to 1 mod 5 and 4 mod 5 are allowed in that particular partition. So this is the generating function of such a partition. Here it's 2 mod 5 and 3 mod 5. But the ones in here are quite interesting in terms of what they are enumerating. So this actually is a generating function of partitions whose parts differ by at least 2. And how does one show that? If it is n square, you can write this as 1 plus 3 plus 5, so on up to 2n minus 1 whole square. sorry, 1 plus 3 plus 5, so on, and then you get n square from there. Here, again, the combinatorial interpretation is that you get, it generates partitions into parts which differ by at least 2, but 1 is not allowed to be a part. But I won't go over these combinatorial interpretations, neither their proofs. Schur was the one who proved them combinatorially. What I would like to do in the remaining 7 to 8 minutes is to give you a flavor of this identity and how it is connected to Rogers-Ramanujan identity. So this is one identity that we have seen right from high school. A formal proof of this goes like this. I consider the left-hand side to be x, and then I see that because this goes all the way up to infinity, this is 1 upon 1 plus, again, x. This is same as this. So x is equal to 1 upon 1 plus x. You solve this quadratic. You see that this is a positive number. So you discard the other root coming from the quadratic equation, and the answer should be 1 plus root 5 upon 2. Such a thing is called as a continued fraction. Of course, one has to prove this rigorously. But now, let us look at what the Rogers-Ramanujan continued fraction is. It's denoted by R of Q. It is given by Q to the 1 by 5 upon 1 plus Q upon 1 plus Q square upon 1 plus so on. So this is really, this part is really with 1, okay, in the denominator. This is just a compact way of writing a continued fraction. Otherwise, if you want to write it traditionally, it will be Q to the 1 upon 5 upon 1 plus all of this. Okay, and similarly, in the denominator of this one, you will have 1 plus all of that and so on. Okay, now this Q to the 1 by 5 looks quite odd, but in the theory of modular forms, this is what turns up. So it's not starting from 1, it's useful to multiply by Q to the 1 by 5. Anyway, it looks like when Q is equal to 1, you get this. But remember, at least for this particular formula, we are having mod Q less than 1. But in that case, we have this beautiful infinite product for this continued fraction. And if you closely look at this infinite product, what does that contain? If I forget about this one in the top, if I take 1 upon Q square Q to the 5, Q cube Q to the 5, that was what was coming from here. And the other one is coming from here. So you are just taking h of Q divided by g of Q, and you are getting this particular product, and you multiply that by Q to the 1 by 5. That is nothing but this infinite product. To get to this, of course, requires quite a bit of effort, but just wanted to point out at the beauty. Now, when you go on the unit circle, so this is in the unit disk, this is what you have. Now, the behavior of this continued fraction on the unit circle, when mod Q is equal to 1, of which this is a particular case. This is quite subtle. The behavior is not known at all points on the unit circle. They are only known at certain regions. Anyway, but what Ramanujan gave in his first letter to Hardy is 2 more evaluations of this Rogers-Ramanujan continued fraction. When Q is e raised to minus 2 pi, he evaluated this explicitly, and with S of Q being minus R of minus Q, he evaluated it at e raised to minus pi, and he got this explicit evaluation. And regarding this, Hardy said, after he received this letter, these formulas defeated me completely. I had never seen anything in the least like them before. A single look at them is enough to show that they could be only be written down by a mathematician of the highest class. They must be true, because if they were not true, no one would have had the imagination to invent them. Where do we get Rogers-Ramanujan identities? Lie algebras, statistical mechanics, partition theory, modular forms, algebraic geometry, K-theory, conformal field theory, group theory, Kac-Moody-Virasoro algebras, knot theory, orthogonal polynomials, probability. In fact, Rogers' work was through orthogonal polynomials. And one simple corollary of Rogers' work was these two identities, which are now known as Rogers-Ramanujan identities. But Rogers had a lot more in his paper, just that the paper was not written very well. One very eminent mathematician whom we lost last year, Richard Askey, once told in a lecture in which I was present that Rogers wrote 3 papers, part 1, part 2, and part 3. If you want to really understand what is given in those papers, try reversely. First read part 3, then part 2, and then part 1. So that's how they have written, so very badly written. Also in transcendental number theory, you get Rogers-Ramanujan identity. To end my talk, I would say that we have only discussed the very basics of this beautiful area of mathematics. And I'll end my talk with a nice quote by J.J. Sylvester. He said, "Partitions constitute the sphere in which analysis lives, moves, and has its being. And no power of language can exaggerate or paint too forcibly the importance of this still recently most neglected, but vast, subtle, and universally permeating element of algebraical thought and expression." Thank you.